Timestamp: March 11, 2003. Eglin Air Force Base, Florida. The Iraqi Republican Guard had a saying that circulated through their ranks in the winter of 2003. The Americans fight from the sky because they are afraid of the ground. Officers in Saddam's military repeated it in briefing rooms and bunkers across Baghdad, Tikrit, and Basra. They had studied American air campaigns, the precision strikes of Desert Storm, the surgical bombing of Belgrade. They understood JDAMs and cruise missiles. They had built their defenses accordingly: deep bunkers, reinforced concrete, tunnels bored into mountainsides. They believed they knew exactly what the Americans could drop from the sky, down to the last pound of explosive yield. They were wrong by about 21,000 pounds. Staff Sergeant Maria Colon was working the flight line at Eglin that morning when she first saw it. She'd been loading munitions onto aircraft for 6 years and thought she'd seen everything the Air Force could strap to a wing or shove into a bomb bay. But this thing sitting on the tarmac didn't belong on a wing. It didn't fit in a bomb bay. It barely fit inside the cargo hold of a C-130 Hercules. It looked less like a weapon and more like a municipal water tank someone had painted olive drab and fitted with grid fins. She remembers turning to another crew member and asking a question that, in retrospect, captured the entire philosophy behind the weapon. How do they aim it? They didn't. Not the way she meant. That was the point. The weapon was designated GBU 43/B Massive Ordnance Air Blast, MOAB. The press would call it the mother of all bombs, a name the engineers at the Air Force Research Laboratory at Eglin neither encouraged nor corrected. It weighed 21,600 pounds. Its warhead contained 18,700 pounds of H6, an explosive composition roughly 1.35 times more powerful than TNT by weight. When detonated, it would produce a blast radius of approximately 1 mile, not a 1-mile kill radius for structures. A 1-mile blast pressure wave that would flatten reinforced positions, collapse tunnel systems, and create an overpressure effect that would reach into hardened bunkers the Iraqis believed were untouchable. But the engineering challenge that consumed the team at Eglin wasn't the explosive. Making a big bomb is, in relative terms, simple chemistry. The problem was delivery. No fighter jet in the American arsenal could carry it. No bomber's internal bay could hold it. The B-2 Spirit, the most advanced bomber on the planet, had a payload capacity of 40,000 pounds, but a bomb bay designed for multiple smaller munitions, not a single object the size of a minivan. The weapon was too large, too heavy, and too awkwardly shaped for any conventional delivery method the United States Air Force possessed. So, a small team of engineers proposed something that sounded, to the Pentagon officials who first heard it, like a joke. They would roll it out the back of a cargo plane. Most people will never hear this story in a documentary or a blockbuster film. The real engineering behind weapons like this is too technical for Hollywood and too unglamorous for the nightly news. That's exactly why channels like this one exist, to tell the stories that actually happened the way they actually happened. If that's the kind of thing you want more of, a like and subscribe are what keep it going. And drop a comment telling me which weapon system you think deserves its own deep dive. The C-130 Hercules was a transport aircraft. It carried pallets of supplies, Humvees, sometimes paratroopers. It was not a bomber. It had no bomb bay, no targeting computer for ordnance release, no hardpoints. What it did have was a rear cargo ramp that opened in flight and a long, flat cargo floor designed for heavy loads to slide along on rollers. The engineers at Eglin looked at that ramp and saw something the aircraft's designers never intended: a bomb release mechanism. The concept was called airdrop delivery. The MOAB would sit on a pallet cradle inside the cargo hold, secured by the same restraint system used for supply drops. At the designated coordinates, the loadmaster would release the restraints. A drogue parachute would deploy from the tail of the weapon, pulling it backward along the rollers and out the open ramp into the sky. Once clear of the aircraft, the cradle would fall away, GPS-guided fins would deploy, and the weapon would navigate itself to the target. The sound of a MOAB leaving a C-130 is not what you'd expect. There's no explosive roar, no thunderclap of ignition. What the crew heard during the first live test at Eglin was mechanical. The clatter of roller bearings under 11 tons of dead weight, the snap of restraint bolts shearing on command, and then the deep, sucking rush of air as the cargo ramp swallowed sky and the weapon slid backward into nothing. The loadmasters described a strange sensation. The aircraft lurching upward as though relieved, suddenly 11 tons lighter in a span of 2 seconds. That first test happened on March 11, 2003, 9 days before the invasion of Iraq began. The timeline was not a coincidence. The MOAB program had been accelerated from a normal development cycle of several years down to roughly 9 months. The Air Force Research Laboratory had begun serious work on the concept in late 2002, when Pentagon planners realized that the coming campaign in Iraq would involve a specific tactical problem: large, dispersed formations of troops and equipment positioned in open desert terrain, supported by hardened underground command facilities. Existing bunker busters could handle the underground targets. But for the surface formations, columns of armor, staging areas, trench networks stretching across miles of flat ground, planners wanted something with a different kind of physics. A conventional bomb destroys through fragmentation and localized blast pressure. The MOAB destroys through atmospheric overpressure across a wide area. The distinction matters. A 2,000-pound JDAM hits a single building and levels it. The MOAB doesn't hit a building. It detonates above the ground, a technique called height of burst optimization, and converts its 18,000 pounds of H6 into a pressure wave that moves outward in every direction at roughly the speed of sound. Everything within that radius doesn't just break. It experiences a sudden, massive change in atmospheric pressure that collapses lungs, ruptures organs, and flattens structures not through impact, but through physics that operates more like weather than warfare. The GPS guidance system was critical to making this work. The weapon needed to detonate at a precise altitude above the ground. Too high, and the overpressure dissipates before reaching surface targets. Too low, and the blast craters the earth and wastes energy downward. The engineers calibrated the fusing system to trigger detonation at approximately 6 feet above ground level, a height that maximized the lateral spread of the pressure wave while maintaining lethal overpressure out to the weapon's effective radius. The March 11th test confirmed the physics. High-speed cameras captured the detonation from multiple angles, a white flash followed by an expanding sphere of superheated gas that flattened test structures arranged in concentric rings around the impact point. The mushroom cloud rose to 10,000 feet. Seismographs at nearby monitoring stations registered the blast as a minor earthquake. But what happens to a weapon that was built for a war it never fought in? The MOAB was ready. The physics worked. The delivery system worked. The GPS guidance worked. And then the invasion of Iraq began on March 20th, 2003, and the bomb stayed in Florida. The shock and awe campaign that opened the war relied on precision: Tomahawk cruise missiles threading through Baghdad's skyline, laser-guided bombs entering specific windows of specific buildings on specific streets. The strategy was surgical, designed to decapitate Iraqi command and control while minimizing the kind of collateral damage that had haunted American military operations since Vietnam. A weapon that erased everything within a mile radius was the opposite of surgical. It was a scalpel war, and the MOAB was a sledgehammer. This created an unusual problem for the engineers at Eglin. They had designed, built, and tested a weapon in record time to meet a specific operational need, and now that need had evaporated, not because the weapon failed, but because the nature of the conflict shifted underneath it. The large, dispersed Republican Guard formations that the MOAB was meant to destroy never materialized in the way Pentagon planners had expected. Some units surrendered. Others dissolved into the civilian population. The massed armor columns that were supposed to meet American forces in the open desert simply never showed up. The war the MOAB was designed for turned out to be a different war than the one that actually happened. So the weapon entered a kind of strategic limbo. It existed. It worked. Everyone knew it worked. But no commander requested it, no mission profile called for it, and no theater of operations presented a target that justified its use. For 14 years, the MOAB sat in inventory, maintained, occasionally discussed in classified briefings, referenced in War College seminars about conventional deterrence, but never loaded onto an aircraft for anything other than a test. It became something rare in the American arsenal, a weapon whose primary value was the fact that everyone knew it existed. Military theorists have a term for this. They call it deterrence by capability. The idea that possessing a weapon influences enemy behavior even if the weapon is never used. The MOAB's existence forced adversaries to account for it in their planning. You couldn't mass troops in the open if the Americans had something that could erase a square mile of terrain in a single detonation. You couldn't build surface-level staging areas or supply depots without considering the possibility. The weapon didn't need to fall to reshape the battlefield. It reshaped the battlefield by sitting in a warehouse at Eglin Air Force Base, maintained by technicians who had never seen it used outside of a test range. This is a strange form of engineering success. The team that built the MOAB solved every technical problem they were given: the delivery mechanism, the guidance system, the explosive yield, the height of burst calibration, and produced a weapon that worked exactly as intended. And then that weapon spent more than a decade doing nothing. In any other engineering discipline, this would be considered a failure, a bridge that no one drives across, a power plant that never connects to the grid. But in weapons engineering, a bomb that never drops can still be the most effective tool in the arsenal, precisely because its purpose was never limited to the moment of detonation. The engineers understood this. Albert Weimorts, the principal designer of the MOAB at the Air Force Research Laboratory, rarely spoke publicly about the weapon. When he did, he avoided the dramatic language that journalists favored. He didn't talk about mushroom clouds or blast radii. He talked about the engineering constraints, the weight distribution problems, the aerodynamic challenges of guiding something that shape through turbulent air behind a cargo aircraft, the materials science involved in building a casing strong enough to survive the drop, but thin enough to maximize explosive payload. For Weimorts, the MOAB was an engineering problem that he solved. What happened to it afterward was someone else's department. But someone else's department eventually came calling. In early 2017, American Special Operations Forces in eastern Afghanistan were fighting a persistent and deeply entrenched enemy in the Achin district of Nangarhar province. The Islamic State, Khorasan province, the Afghan affiliate of ISIS, had moved into a network of tunnels and fortified cave complexes originally built during the Soviet-Afghan War in the 1980s. These weren't simple caves. They were engineered tunnel systems with reinforced entrances, multiple chambers, ventilation shafts, and interconnected passages that allowed fighters to move underground across significant distances. Conventional airstrikes could collapse an entrance, but the fighters inside would simply move deeper into the network and emerge from another exit. The tunnels were, in a tactical sense, the inverse of the problem the MOAB was designed to solve. Not troops massed on the surface, but troops hidden beneath it. On April 13, 2017, at 7:32 p.m. local time, a MC-130 aircraft, the special operations variant of the Hercules, upgraded with terrain-following radar and electronic countermeasures the original transport was never designed to carry, reached its release coordinates above the Achin district. The loadmaster initiated the sequence. The restraints released. The drogue deployed. And for the second time in 14 years, a MOAB slid backward along roller bearings, off a cargo ramp, and into open air. The crew felt the aircraft jump. 11 tons gone in 2 seconds. The same lurch the test crews had described at Eglin, except this time, there were no high-speed cameras arranged in concentric rings below, no seismographs positioned at measured distances, no engineers watching from bunkers with clipboards. Below was a valley in eastern Afghanistan, where an unknown number of ISIS-K fighters occupied a tunnel network that had already survived decades of war against 2 superpowers. The weapon fell for approximately 6 seconds before its GPS fins corrected its trajectory and it reached its calibrated detonation altitude. What followed lasted less than 1 second and was visible from 20 miles away. The pressure wave entered the tunnel mouths at roughly the speed of sound, not as fire, not as fragmentation, but as a wall of compressed atmosphere that moved through the underground passages the way water moves through pipes. The overpressure didn't need to collapse the tunnels to be lethal. It moved through them. Every chamber, every branching corridor, every ventilation shaft that the tunnel builders had engineered as an escape route became instead a channel that carried the blast deeper into the network. The very features that made the tunnels survivable against conventional weapons, their depth, their interconnection, their multiple exits, became the mechanism of their destruction. The air itself became the weapon inside those passages. The Afghan government reported 94 ISIS-K fighters killed. No civilian casualties were confirmed in the immediate assessment. The tunnel complex, which had resisted months of conventional strikes, was rendered unusable in a single detonation. General John Nicholson, the commander of U.S. forces in Afghanistan, described the strike in measured, almost bureaucratic terms. "We targeted a system of tunnels and caves that ISIS fighters used to move around freely," he told reporters. He did not mention the engineering. He did not mention the 14 years. He did not mention that the weapon had been designed for a completely different war against a completely different enemy on a completely different continent. That gap between what the MOAB was built for and what it ultimately did is the part of the story that rarely gets told. The engineers at Eglin designed a weapon to destroy Republican Guard formations in the Iraqi desert. Instead, it destroyed a tunnel network in the Afghan mountains. The physics were the same. The overpressure was the same. The delivery method was the same. But the tactical context was inverted. A weapon designed to kill what it could see ended up killing what no one could see. The surface blast weapon became, through the accident of geography and the geometry of tunnel systems, the most effective underground weapon the United States had ever deployed. Not because it penetrated the earth, but because it didn't need to. It sent the blast through the front door. There's an irony the engineers would probably appreciate if they were the type to dwell on irony. The MOAB's guidance system, the GPS fins, the height of burst calibration, all that precise engineering designed to detonate the weapon at exactly 6 feet above ground level, was optimized for flat, open terrain, the Iraqi desert. Instead, the weapon detonated above a mountainous valley riddled with cave entrances, and the terrain did something the engineers never modeled. It funneled the blast. The valley walls reflected the pressure wave. The cave mouths channeled it underground. The weapon performed better against the Afghan tunnels than it would have against the Iraqi formations it was designed for, and it performed better for reasons that had nothing to do with the engineering and everything to do with luck, timing, and the strange recursion of a 30-year-old Soviet tunnel network meeting a 14-year-old American bomb that had been waiting in a warehouse in Florida for a war that finally matched its physics. Albert Weimorts died in 2005. He never saw his weapon used in combat. He never saw the Afghan strike, never saw the footage, never knew that the engineering problem he solved would find its answer in a place he never designed it for. Weimorts kept a notebook, not a classified one. The classified work stayed in the lab, but a personal notebook where he sketched problems the way some people sketch landscapes. Weight distributions. Center of gravity calculations for an object that had to remain stable while sliding backward on rollers through turbulent air. His colleagues at the Air Force Research Laboratory said he worked on the MOAB the way a carpenter works on a cabinet, with patience, with measurement, with a fixation on tolerances that other engineers considered excessive. He wanted the casing walls thinner. He wanted the explosive fill denser. He wanted every pound of structural weight converted into a pound of payload, because every pound of steel that survived the detonation was a pound of energy wasted on holding the bomb together instead of killing something. This is the part that doesn't make the news cycle. The headline said, "Mother of all bombs." The cable news graphics showed mushroom clouds and blast radius overlays superimposed on Manhattan for scale. The Pentagon briefings used words like capability and strategic asset and force multiplier. None of them talked about the notebook. None of them talked about the months Weimorts spent arguing with metallurgists about the tensile strength of the bomb casing, or the weeks he spent redesigning the cradle system because the first version's roller bearings couldn't handle the lateral forces during extraction. The weapon that the world saw as a symbol of overwhelming American power was, to the man who built it, a sequence of stubborn problems, each solved before the next one would sit still. He would have understood the Afghan strike better than anyone, and he would have understood it differently than anyone. Not the politics, not the strategic messaging, not the footage or the mushroom cloud or the 94 dead. He would have understood that the weapon detonated at 6 feet above ground level in a mountain valley, not the flat desert he'd optimized for, and that the overpressure behaved in ways his models never predicted because his models assumed open terrain with no reflective surfaces. He would have wanted the data. He would have wanted to know what the valley walls did to the pressure wave, how the blast propagated through tunnel geometries he never tested, whether the casing thickness he'd fought so hard to minimize made any difference at all when the physics found a landscape that amplified everything he'd built. He would have reached for the notebook. He would have started sketching. The notebook is a standard government-issue composition book, black cover, 79 cents from the base exchange at Eglin. Nothing about it suggests it belonged to the man who designed the largest non-nuclear weapon in the American arsenal. The pages are gridded, not lined. Weimorts preferred graph paper because it let him sketch to rough scale without reaching for a ruler. The handwriting is small, mechanical, the letters formed with the same precision he demanded from his casing tolerances. On one page, dated February 2003, there's a center of gravity diagram for the cradle system showing the exact point where 11 tons of explosive would balance on a set of roller bearings inside a C-130. He circled it 3 times. His colleagues kept working after he died. The weapon he designed kept sitting in its warehouse, maintained by people who understood what it could do because he'd shown them. And when the call finally came in 2017, when a commander in Afghanistan needed something that no other weapon in the inventory could deliver, the MOAB worked exactly the way Weimorts said it would. The drogue deployed, the cradle separated. The GPS fins guided it down. The detonation height was 6 feet, just as he specified. Every tolerance he obsessed over, every pound of casing he argued away, every roller bearing he redesigned, all of it performed in combat the same way it performed in testing, because he built it to a standard that didn't distinguish between the two. The MC-130 crew that dropped the weapon over Achin district flew back to Bagram airfield that night. The aircraft commander was a lieutenant colonel whose name remains classified. In a debrief that was later partially declassified, he described the moment of release in terms that had nothing to do with strategy or geopolitics or the war on terror. "The aircraft jumped," he said. 11 tons just gone. You feel it in your spine. And then you turn the aircraft and you look back and the whole valley is lit up like daylight. Just white. Pure white. And you think, we built that. Americans built that. The battle damage assessment took 3 days. Surveillance drones mapped the blast area in overlapping passes, building a composite image of what the valley looked like after. The tunnel entrances that had survived years of conventional strikes were gone, not collapsed, not blocked, but scoured. The ground itself had been rearranged. 94 confirmed dead, 0 civilians. 0 friendly casualties. The ISISK network in Achin district never recovered. Within 6 months, the Afghan government declared the district cleared. General Nicholson held a press conference. He stood in front of a map of Nangarhar province and pointed to the Achin district with a laser pointer and said the strike achieved its intended purpose. A reporter asked if the MOAB was the right weapon for the target. Nicholson didn't hesitate. "It was the right munition for the target," he said. "The tunnel complex was extensive. It was well defended, and now it doesn't exist." A staff sergeant who served in Achin before the strike, who had watched conventional bombs hit the same ridgelines for months while ISIS fighters simply moved to the next tunnel, was interviewed for an Army oral history project later that year. He talked about the frustration of fighting an enemy that lived underground, that absorbed punishment and reappeared, that turned the earth itself into armor. Then he talked about the morning after the MOAB. "We walked the site," he said, "and there was nothing left to walk to. 14 years that thing sat in a warehouse, and it worked the first time they needed it. First time. That's American engineering."